You're going pretty far.
I'm big.
So number 6, things you can use to describe this. You can have the event plus the complement equals 1. You can have 1 minus the event equals the complement, or you can have 1 minus the complement equals the event. And those probably aren't written perfectly as far as the mathematical goes, but that's all it's saying. So event, let's say you want to get a 1 on a die, that's your event. The probability would be 1 out of 6. The complement of that would be 5 out of 6. It's got a total up to 1 here. 1 minus the event's 1 out of 6. Well, 1 minus 1 out of 6 is 5 out of 6, and then turn it around to be that way. Other questions?
45.
45. The access code for a garage door consists of 3 digits. Each digit can be any number 0 through 9, and each digit can be repeated. Find the number of possible access codes. What's the probability of, so on, so on, so on. We'll read them as we go. So we got 3 digits on our access code. When I'm doing a problem like this again, if I'm doing 3 things, I make 3 blanks. 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I highly suggest, I don't do this stuff. I don't write this stuff out and make these blanks and stuff because I enjoy doing all of this. I do it because it helps. Makes it easier for me to think it through. I know Cody's probably, his IQ is about 10 times higher than mine, so he doesn't need to do all that, but I would suggest it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many choices do I have for the first position here then?
10.
Second one? 10. So it's 10 for all of them. Sometimes that'll change depending on, if they say that you can't repeat the numbers or whatever, you got to read the problem. This time it said the numbers can repeat. So to get the first part, all we're going to do is multiply all those. What's 10 times 10 times 10?
1,000.
So that's the possible outcomes. Let's see here. What is the probability of randomly selecting the correct access code on the first try? So you got some access code. That's my access code. You can't see it. What's the chances or the probability that you get it correct on the first try?
1 out of 1,000.
1 out of 1,000. Part C. What's the probability of not selecting the correct access code on the first try? That would be the complement of it. 999 out of 1,000.
Wait, so how would you know when it's the complement? Like,
So here, I should have wrote this out. Probability you're not correct. Well, there's only 2 things that could happen. Either you get it correct or you don't, right? So those 2 are complements of each other. So it'd be like picking a student in this classroom. Either I'm going to get a male or I'm going to get a female. All right? There's no other choice. One's got to be the complement of the other. So they all got to add up to the total. And here, all we do, since it's not, we just take this, 1 minus that, which is going to leave us with 999 out of 1,000. So these 2 are complements of each other because together they add up to the whole situation. Does that make sense?
yeah.
Next question.
18.
18. Says identify the sample space. Identify the sample space of the probability experiment and determine the number of outcomes in the sample space. Draw a tree diagram if it is appropriate. So you can draw a tree diagram if you want. You don't have to. You guys want to draw a tree diagram for this one, or you want me to do it some other way?
Can you just do
Whatever
it?
feels right to you. sir.
Okay.
Can you do a tree diagram?
Do a tree diagram. So we're tossing 3 coins. If we're tossing 3 coins, first coin, you could get a what? Or that's the first coin. Second coin, you got a head the first time. What could you get on the second coin?
Heads.
Got a tail the first time. What could you get on the second coin? Third coin, got a head the first time. You could get a what?
Head again.
Head or tail. Next one.
Tails or head?
Michael will probably do that on the next test, and then it'll mess him up, and he'll wonder why.
I got it wrong.
So that's our 3 coins, our sample space. We're going to list it out here. What do we get this first route?
All heads.
Heads.
About the second route.
Head, tail.
Tails.
Third route.
Heads. Tails.
Fourth route.
Tails.
Fifth route.
Tails, head, head.
Sixth route.
Tails.
Seventh route.
Tails.
No, tails,
Oh,
tails,
tails, head, my God. I thought you said.
And last route.
Tails.
So that's our sample space. They wanted that listed out. They also wanted you to come up with how many there are. How many are there? 8. So there's 8 total outcomes. Be able to list the sample space like this. Now, again, if you didn't do a tree diagram, you gotta be real careful and make sure that if you didn't do the tree diagram, when you're listing them, that you're listing everything. All right, because if you don't do the tree diagram, which this tree diagram wasn't all that difficult, if you don't do it, and you're going through and you're saying, okay, I could get 3 heads, I could get a head and 2 tails, and as soon as you get to that point, you're gonna miss something. All right, it's just, it's probably better off on this one to do the tree diagram. Unless you've done these for a long time, like if I was doing it and I didn't want to make the tree diagram because I was being lazy at that moment, I know that I have 3 heads, that's supposed to be H. Then I'd go heads, tails, heads, then I'd go heads, heads, tails, and I would do them putting in 1 tail in those 2 spots, and then continue on from there with like 2 tails. Oops, not 2 tails that way. Tail, head, tail, and then tail, tail, head. So I got ones with 1 tails here, ones with 2 tails here. Then you'd have a 3 tail, and even now,
You're still getting confused.
I'm getting confused because I'm missing something. What am I missing? Because I only got 7, so.
Tails. Head.
Tails, head. So I missed that one over here. So a lot of times it might be better to draw a tree diagram. Come up with them. Other questions?
What about the simple past?
Where are we at?
22.
There's a few of them on there, but I just couldn't remember how to.
If it's simple, it's just got one possible thing, all right? So it would be something like if let's just take this as an example. If I would say I wanted the probability that I got a head, then a tail, that's one simple event. So that'd be 1 out of 8. I could say that maybe I wanted the probability that I got 2 heads. Well, this one has 2 heads, but so does that one. Well, maybe you don't even count that one. So does that one. So does this one. Right? So there's 3 of those. That wouldn't be a simple event because you got 3 different things that could happen. Does that make sense? Other questions? Nope, we're just ready. Did you find one, Jenna?
40. The probability experiment, that's like 41 and 42.
Says a probability experiment consists of rolling a 6-sided die and spinning a spinner shown at the left. The spinner is equally likely to land on each different color. Use a tree diagram to find the probability of each event. Tell whether the event can be considered unusual. Remember, what makes an event unusual? What percentage?
Unusual is low.
So 0.05 or less. That's unusual. All right. Now, what you 0.50 or less is unlikely to happen. All right. So don't get those two confused. Yeah. So unusual means the events are probably not going to happen ever. Okay. Unlikely just means if we were betting on it, you'd be better to bet the other way than this way because more than or less than 50% of the time you're going to win. So let's see, this is probability experiment. 6-sided die, so I'm going to go ahead and make myself a tree diagram again because you can see my mind must not be what it is because I couldn't remember what I missed there. So if I roll my die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. And then if I spin the spinner, if I roll the die, how many possible outcomes on the spinner? 4. What's it? Yellow, green, blue, red?
Yeah.
So we'll just go yellow, green, blue, red. If I rolled a 2, same thing, right?
Here.
Yellow, green, blue, red. Roll 3, same thing. Yellow, green, blue, red. I roll 4. Yellow, green, blue, red. Roll 5. Yellow, green, blue, red. And if I roll 6, yellow, green, blue, red. If I listed all these, I could get 1 yellow, 1 green, 1 blue, 1 red, 2 yellow, 2 green, 2 blue, 2 red, 3 yellow, 3 green, 3 blue, 3 red, 4 yellow, 4 green, 4 blue, 4 red, and I know what's going through all your minds is, gosh, this is stupid, me listing all those out. If it helps you, especially on a test, Number one, it's taken me all about 2 hours to do this so far, right? It doesn't take that long once you just do it. And don't sit and go, oh God, I don't want to do all that. And sit and worry about it. It takes you longer to worry about it than it does to actually do it. 5 yellow, 5 green, 5 blue, 5 red, 6 yellow, 6 green, 6 blue, 6 red. So those are all our possible outcomes. This is all our sample space. All the things that could happen. 41. We'll just run through them all if you want. 41 through 44, or whatever it is. Somebody will help me out and tell me what's 41 say. Probability of what?
Event A, rolling a 5 and the spinner landing on blue.
So we want just 5B, right? So we look down through here. How many 5Bs do you see? Out of a total of, how many are there? 4, 8, 24. That's our answer to 41. Could change it to a decimal if you wanted. I would leave it as that fraction. What's 42 say?
Rolling an odd number and spinner landing on green.
So odd number and green. So we go down through here, and usually if I have the sample space drawn out here, I just circle the ones that are favorable outcomes. So we want probability odd green. How about this one? Does that work?
No.
Yes.
No.
B.
Yes.
Yes.
No.
So how many?
3.
Out. And that'll reduce to 1 out of 8. And again, you could change that to a decimal if you wanted. The book probably changed it to a decimal if one of these answers was in the back of the book and you looked it up. 43, what's it say?
Rolling a number less than 6 and it landing on yellow.
Number less than 6 and it landed on yellow. So now the only bad thing with doing it this way is I've already circled some of them. Those don't count anymore. So we want a number less than 6 and yellow. Which ones are that going to be?
1 through 2, 1 through 5.
So that one, that one, that one, that one, that one. How many of those are there?
5.
So probability less than 6 and yellow 5 out of 24. That won't reduce, but again you could change it to a decimal if you wanted. And 44, what's it say?
Not rolling a number less than 6 and it landing on yellow.
Not rolling a number less than 6 and it landed on yellow. So a number not less than 6.
So 6, right?
So just
So it's yellow.
So the only one possible is 6, right?
So it'll be 1.
And yellow, so how many of those are there?
Just 1.
Just one. 1 out of 24. What's the probability, this isn't on there, but what's the probability of not getting 5B?
23.
And this event would be complements of each other. So if you remember that, if they say, okay, what's the probability of not getting 5B? Probably don't want to go through here and circle all the ones that are not 5B. That's too many of them. So if you say, okay, if I don't want to get 5B, get rid of 5B, what's my probability of getting any of these others? So you're just doing the complement. All right, what we're going to cover today, conditional probability and the multiplication rule. Conditional probability and multiplication rule. While you're getting stuff out. Determine conditional probabilities. That's what we're going to cover. Distinguish between independent and dependent events. We'll talk about that. Hopefully you know what independent means and what dependent means. Use the multiplication rule. It's not too difficult. It's just multiplying. And use the multiplication rule to find conditional probabilities. That's the title, conditional probabilities. Put all this stuff up here. And I went too far. As we get into these probabilities, some of them get sort of confusing when you're dealing with independent, dependent events, and what we'll cover here in the next couple of classes, because they get to where you can get confused and get things mixed up. This is very important here. Probability. This is just saying the probability that you get event B, whatever it is, that's got a slash, given the A. This, that second letter there, or that second event, it's telling you that's where you're picking from, or it already has happened. What I mean by that is, I might say something like, what's the probability of drawing a name out of the hat and picking Braden if I only put the males in the classroom names in the hats? All right? So it'd be 1 out of 4. But now what I'm doing there is I'm saying I'm only picking from the males. So if we had a list, male, female, and maybe over here to the side we had something else that went along with it, maybe pretty and ugly, and we put everybody's in there somewhere. All right? Don't smile, Riley. I'll stick your name up there real quick.
Yeah, that's a good one.
So we stick that in there, then what we're saying, if we're going to pick Braden's name, we want to pick Braden's name, we're only picking from this part. So we're not picking from the entire group. So some events already occurred. That's a conditional probability. Again, this is red. Probability, event B happens, or that we get event B, whatever it is, given that we're just picking from A, or A's already occurred. Independent, dependent events. What do you think an independent event or independent events are?
It does it without. It doesn't sound like.
All right. Does not rely on each other. They do not rely on each other. Each other. And if they're dependent events, what do you think that
It
is?
has to happen for that.
All right, dependent events means one affects the other. Okay? So one event affects what the other event could be. 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced. So if we got a deck of cards and we're drawing from that deck of cards, and we draw, find the probability the second card is a queen given the first card was. So our probability is going to look like this. Probability that we get a queen given that we already have what laying here in our hand? A king. Are those 2 events independent or dependent?
Picking the queen.
All right, because what we've already done affects what's going to happen here. All right? So what's the probability of getting that queen? 4 out of, how come 51? All right, and if you're not sure, this might be something that we need to write down now. If, in the past, a lot of the students I've had in this class haven't known a whole lot about a deck of cards. You know, I don't know. Don't go home and get me in trouble religious-wise or something if you're not allowed to mess with cards. Just, all right, that's what we use. Different things with cards. First of all, there's 52 cards in a deck. How many suits?
4.
4 suits. How many cards in each suit?
4. Or no, hold on. 12, yeah.
Close.
13.
13.
13 in each. So there's 13 cards in each suit. What are the suits? Clubs.
Spades.
See if I can make a club.
Heart.
That's a club. Spade. Looks something like that. Hearts
Diamond.
and diamonds. So 4 different suits. What do you know about these 2?
The red.
They're red. These 2 are black. Let's see what else. How many face cards in a whole deck? 12 face cards. Don't consider an ace a face card. It doesn't have a face on it. What are those face cards?
Jack. Queen, king.
Jack, queen, and king. What else? What else? Could we do? How many red cards? 26. How many black cards? 26. Hopefully, if you know all that. Again, going back to this, dependent, because we kept the king out. What if we replaced the king?
It'd be 4 out of 52.
Then it'd be 4 out of 52, and if the first event wouldn't affect the second event. So they'd be independent. And notice how we were supposed to tell on that other one. Notice this event on that one problem, we were supposed to tell if it was unusual or not, and I didn't do it. Is this event unusual?
Higher than 0.5.
It's higher than 0.05, right? So not unusual. We were on 41 through 40 whatever, we were supposed to tell if they were unusual or not, and I didn't do it.
Unusual is if it's below.
If it's below 0.05.
That would be unlikely then, right?
Right, this event's unlikely because it's lower than 50% of the time. But just make sure, it's just easy to get confused. Instead of 0.50, it's 0.05. Table shows the results of a study in which researchers examine a child's IQ and the presence of a specific gene in the child. Find the probability that the child has a high IQ given the child has the gene. So right away, we're looking at this, and when we say this, it's the probability that they have a high IQ given that they have the gene. So when you're reading this, you got to be really careful. Are we choosing from all 102 of these people?
No, just
We're just saying we're only picking from the people who have, so we're just looking at that group right there. All right? So we want the probability that they have a high IQ. How many of those have a high IQ?
33.
33 out of
72.
72. And we probably change that into a decimal just by dividing it. It looks like it's probably, what, about 45% or something like that maybe?
that's a little under this.
Somewhere close to that. But the main thing here, you're just looking at that group. Now, if they just said, what's the probability that somebody has a high IQ out of the group, then we're taking that total, and we want the total of people with high IQs, which is right there, so it'd be 52 out of 102.
What's technically like a high IQ? What are they like?
I think like 110 or 115 or something like that. So there are 72 children. Notice they lightened this part up over here because we're not even looking at that. We're just picking from this part of the group right here. So 33 out of 72.
There's a test
There's a test you can take. Comes up to be about 46%. Independent events. Independent events. The occurrence of one event does not affect the probability of the occurrence of the other event. On this formula, I'll give you a second to write some of this down. Again, don't write things down word for word. Otherwise it takes too long. Write down what helps you. I say that, and then if it helps Jenna to write down every word, then I guess that's what you do.
Fantasy football.
I'm talking until dinner. It's like he texted me the other night. What do you want to check this?
You just go crazy for a minute.
My defense killed me.
Yeah, facts.
So we taking this symbols quiz next time?
We do Friday.
Friday.
Friday? I won't be able to get it in before
Oh,
interview.
come on,
We do it
come
Friday.
on, guys, please.
I don't care to do it next time.
I guess we'll do
Well,
it.
what's like, it's just the symbols like from all chapters or just from?
Yeah, everything.
Do you have a review paper for that?
We have notes that we can look on that quiz.
No.
No.
No. Symbols is no notes. We could go over some of them, like
Yeah.
maybe at the end of the day today or something.
I won't read it.
So if we look back at the last one with the probability of getting a queen given that you had already drawn a king. It changed the probability of getting that queen and made it 4 out of 51. If we just look at the probability of getting a queen, what's the probability of getting a queen from a deck of cards?
4 out of 52.
What this is saying is if the events are independent of each other, if they do not affect each other, then when you set it up this way, the probability of getting B given that A's already occurred, then the probability that B occurs shouldn't be affected. It should be the same as it would have been without even messing with all that. All right? So it might be something like, what's the probability, I flip a coin twice, what's the probability of getting ahead given that the first flip was ahead? What's the probability of me flipping that coin the second time and getting ahead?
Still a half.
Still 1 out of 2. Alright? So the probability of head, given that a head's already occurred, is the same as just the probability of getting a head on no matter what flip I'm on. Those are considered independent events, because when I flip the coin the first time, just because it came up on heads doesn't mean that that changes it and it's got to come up on tails the next time. So this event, probability of getting A, given that B's already happened, is going to be the same regardless of what B was. Independent events. Events that are not independent or dependent. Example, if I draw a 10 from a deck of cards, then draw another 10 from the same deck. First of all, so if I, probability that I draw a 10, given that I've already drawn a 10. These are dependent events if I don't do what with this first 10?
Put it back.
If I don't put it back. So the probability of getting that second 10, given that I don't put it back, would be what?
3 out of 51.
3 out of 51. Probability of getting that second 10, if I put the first 10 back, is how much?
4 out of 52.
4 out of 52. So here, these would be dependent events. This way they would be independent events. Decide whether the events are independent or dependent, selecting a king from a standard deck, not replacing it, and then selecting a queen. We already talked about this, independent or dependent. Dependent. And the way they're deciding it, they're looking at probability of just getting the queen is 4 out of 52. Probability of drawing a king, then a queen. Probability of getting that queen is 4 out of 51, so those events, or the probabilities change, so that means they have to be dependent. One affected the other. Tossing a coin and getting a head, and then rolling a 6-sided die and getting a 6. Independent. Does flipping the coin affect what's going to happen on the die? No. And if you look at it, probability of rolling a 6 on the die is 1 out of 6. Probability of rolling a 6 on the die after you got a head on the coin, still 1 out of 6. Multiplication rule. Multiplication rule is pretty important. All it's really saying is you write it down is you're going to take the probability of one event and times it by the probability of the second event to get the total probability of getting both things. Or 3 events, or 4 events, or 5 events, however many you want to go out to. I think I'll put these 2 on there. What's that symbol mean? Sum, add them all up. Oh no, I'll put that one on there because nobody ever remembers it.
Standard deviations.
Is it there? Something?
Some squares.
Squares.
Sum of the squares. Nobody ever remembers it.
Close.
What do you think?
So on this first one, probability of A and B, all it's going to be, so we want probability we get A and the probability we get B. Let's say we go back to our thing there, probability that we draw a king and then we draw a queen. Don't be writing that dumb on my board. Yeah, right. You're right? Something like that. Ebersole smelly or
It
something.
says Fletcher on it.
So probability of getting a king and a queen. We're sitting playing some game. We want to draw a king and a queen for whatever reason. What's probability of getting a king, first of all? 4 out of 52. All the multiplication rule tells us is the probability of both of these things happening, we just multiply. Now, if we got the king and it's right here in our hand, what's the probability of getting the queen?
4 out of 48.
4 out of,
Would be 48 since you have the queens.
there's still 51 cards in the deck, right?
Oh, I think so. Okay. I thought you took out all 4 keys.
No, you just took out one king,
Okay.
the one that's in your hand. And then all we do is we multiply those. 4 times 4 is 16, and whatever 52 times 51 is.
So you always take one out of it then?
For this, if you're keeping it in your hand. Alright, so if we're playing a game of cards,
Okay, so you're acting when you do the probability like as if you got it.
right, it's already done. So that's what this means. Probability that you get B, probability that we get that queen, given that we already have the king in our hand. If the two events are independent of each other, so if we were replacing the card, what's the probability of getting a king?
Still 4 out of 52.
4 out of 52. If we replace the card, what's the probability of getting a queen?
4 out of 52.
4 out of 52, and we multiply those two together to get that total. Notice it's going to give you two different probabilities. So dependent events, independent events. And with independent events, we could add more stuff onto here. Probability event C happens times probability event D happens, so on, as far out as we want to go. And you just multiply those events together to get the probability of all of them happening all at that one time. Two cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then a queen. We just did that. So it'd be 4 out of 52 times 4 over 51. What do we know about this event?
It's unlikely.
That's not just unlikely, it's unusual. It's unusual. So when and I sit and watch these people playing poker on TV a bunch, and if you watch them play Texas Hold'em, they get two cards. If one of them gets a king and a queen, is that very likely to happen again?
No.
No. Less than 1% of the time is that going to happen. That's why you see these guys that you think, well, they don't have anything. But they got a king and a queen or an ace and a king, and they're betting a whole bunch of money because they have high cards. And it's very unlikely that they're going to get those high cards again. And it's very unusual that anybody else sitting at the table is going to have those high cards. Let's look at this real quick. Because I see them all the time, I think, man, they're betting on that. They'll have a pair in their hands. Let's say they have a pair of 4s. So what's the probability of getting a 4 and a 4? What's the probability of getting the first 4?
4 out of 52.
4 out of 52. What's the probability of getting the second 4?
3 out of 51.
3 out of 51, because there's only 3 4s left, right?
Yes.
I know the top's 12. Somebody help me out. What's 52 times 51?
2,652.
Somebody divide that for us. I guess it was right there, wasn't it?
Yeah.
Somebody divide that for us.
Oh, hang on, Isaac. How did you do that?
12 divided by 2,652.
0.006.
Doesn't work this time, Mike.
We have to get our calculators out.
Yeah.
It's 11:11. Make a wish.
0.0045.
So when they get a pair, they know, and these guys, if you ever watch any of those poker shows, these guys that play this poker on TV and play it for a living, they're not just normal people. These are people who dropped out of Harvard, dropped out of MIT, dropped out of Cal Fullerton or Cal Berkeley. I mean, they're very, very intelligent people who can figure all this stuff in their head. All right? And they know if they got a pair already, the chances of anybody else sitting at the table getting a pair like they have is less than 0.5%. So if they're sitting there with 6 people, 6 other people sitting at the table with them, very unusual that they get a pair and somebody else gets a pair. Very unusual. That's why you see them, I watch them all the time and I say, you got a pair of 4s. Just about anything beats a pair of 4s. Why are you betting so much? Because they know that the chances of somebody else having a pair is less than 0.5%. So if you're looking at this is an example. You and a friend are playing Texas Hold'em poker. The setup for the hand is shown below. Find the probability that you win the hand. This is your hand. This is their hand. Right now, what do you have? You got an ace high. All these cards, just to tell you how to play Texas Hold'em. These are your cards. These are your friends' cards. All these cards down here, you both get to use. And you make the best possible hand. All right? So as of right now, you have a pair of kings and an ace. They have what?
3 kings and a jack.
They have 3 kings and a jack. So they have 3 of a kind. You have 1 pair. 3 of a kind is a whole lot better than 1 pair. Okay? What would have to come up here and here for you to win?
2 aces.
2 aces. So we want this to be an ace. We want this to be an ace. If that happens, then you're going to win. If it doesn't happen, then your friend's going to win. Anything else comes up in there, that's they're going to win. So what's the probability that we get an ace and another ace on those 2 cards?
Well, there's already 1 gone.
So there's already 1 gone. So what's the probability of getting this next card here being an ace?
3 out of.
Now let's count up and see here. There's already 7 cards out on the board, so how many cards are left?
45.
So probability of this one being an ace, 3 out of 45. What's the probability of that second one being an ace?
2
out of 44.
So I know this is 6 on top. Somebody help me out. What's 45 times 44?
1980.
19 what?
80.
Somebody divide that for us. What's 6 divided by 1980? 0.003.
Yeah. So not really good.
Remember, if we change that to a percent, we bump it over 2 places. That's not 3% of the time you're going to win. That's 0.3% of the time. So if we were going to do 100 times, if we did this deal 100 times, you wouldn't even win 1 whole time out of that 100. If we did 1,000 times, you would win 3 times out of that 1,000.
Nice.
So your friend would win 997 times out of 1,000. You're going to win 3 times out of 1,000. Now, if you know how to play cards, you know I screwed this up when I made up this, because anybody see anything else that these could be?
You get like a flush and all that.
So we got 1, 2, 3 hearts. If these came out to be hearts,
You would win.
then you would win with a flush. If one of them wasn't the jack of hearts. Because if it was the jack of hearts, then they would end up with a full house. And that full house beats the flush. And
That
so
beats everything, doesn't it?
full house.
Yeah.
4 of a kind or straight flush.
Crazy.
Yeah. So that's not exactly true, but I don't want to teach you how to play poker. That's not what we're here for, and I don't want anybody going home telling their folks Ebersole was teaching us how to play Texas Hold'em in class. 3 out of 45, we did all this. Second ace, 2 out of 44, comes out to about 0.3%. Coin is tossed and a die is rolled. Find the probability of getting a head and then rolling a 6. Again, if you need to make the tree diagram for this, might be a good thing. Coin is tossed and die is rolled. If I toss a head, what could I get? So head 1, head 2, head 3, head 4, head 5, head 6, right? Sorry, I'm being lazy again. Not writing it all out. Tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. So what's our probability of getting a head and a 6?
1 out of 12.
And that works out that way just because these are independent events. They don't affect each other. Hello? Ah! She's going to think I just don't. Hello? Yes. Sure. Riley, tell her I was getting back there because I know what she's thinking. Ebersole never answers phone. Tell her.
I made your thing pretty true.
Huh?
I made your thing pretty true.
What's that?
The
Oh, yeah.
most likely thing.
So tell her, Ebersole was trying to answer his phone. He just didn't make it back there in time before you hung up the first time. So these are independent events. Just check your email. Everything's on there.
Okay.
2 rounds.
Bye.
So to get the head, it's 1 out of 2. Get the 6, 1 out of 6. We multiply. 1 times 1 is 1. 2 times 6 is 12. Comes out the same as the way we did it using the tree diagram. Look at this event. Is that an unusual event?
No.
No, because that would actually come out to about 8.3%. That's higher than 5%, so it's not unusual.
Wait, so it's 5% unusual
5%
and lower is?
and lower is unusual. Yeah, probably should never even put that up there because what you guys keep thinking of is right here in the middle is 50%, right? And over here is the stuff that's more than likely to happen. Over here it's unlikely to happen. All right? That's just saying if we're going to bet on something, we probably want to bet on events that are on this side because more than 50% of the time we're going to win. But for an event to be unusual, that means it hardly ever happens. That's when it's down here 5% or less. Probability that a particular knee surgeon is successful is 0.85. So 85% of the time you go in for knee surgery, this certain surgeon is successful 85% of the time. Find the probability that 3 knee surgeries are successful. So you go into this knee surgeon. They've already done 2 operations earlier that day. Do those 2 operations affect your operation? Let's hope not.
Yeah, I bet.
All right, if it does, if it's getting late in the day and they started drinking about noon or something and then they operate on you, then yeah, that would affect it. But we hope that's not the case, right? So we hope that you go in there, or the first person goes in there, it's 85% chance that they do the surgery right. Second person's 85%. You go in, and the percent that they do it right is still 85%. So these are independent events, so we should be able to just go probability of success on the first one times probability of success on the second one times probability of success on the third one. And all you got to do here, what's the probability that the first surgery is successful?
85.
0.85. What's the probability the second one's successful? What's the probability the third one's successful? 0.85. Somebody multiply those three together for us.
0.614.
Good enough. So 0.614. Probability that this surgeon goes in, does those three surgeries in that one day, there's about a 61% chance that all three of them are successful.
Oh, no.
I don't know if we go to that search.
I'm not going to that search.
All right? So about 61% chance that all three are successful.
Yeah, I'm definitely not going to that search.
Find the probability that none of the three surgeries is successful. A little tougher. How could we figure out none of them are successful?
So do you take what's remaining after 85 and
Okay, so what would be remaining after 85?
0.15.
So we want the probability that it's unsuccessful times the probability that it's unsuccessful times the probability that it's
Unsuccessful.
unsuccessful. We want all of them. What's the probability that it's unsuccessful?
0.15.
0.15. What's that give us?
0.00.
0.00 what? So is it unlikely that this surgeon's going to have a really, really bad day and all three of them aren't going to work? It's not very likely because it's less than, it's 0.3%. So it's less than 0.5% of the time are all three of them going to go bad. Find the probability that at least one of the three surgeries is successful.
so that's
Now we're getting a little tougher, aren't
Now
we?
do you just do
0.85.
one is unlikely, or
You choose on
one is the 85, the other one's unlikely?
Is that, but what's that going to tell us? If we just do one of them is successful and the other two are unsuccessful, is that going to tell us the probability that at least one is successful? Doesn't work that way, does it? Because if at least one, that means one could be successful, or two, or all three. So how could we do that?
But you just said that it's 100%.
100%?
I don't know.
I have a guess. I might be wrong. Might be wrong. So do you just get the probabilities of each individual one and then multiply it all together? Like, let's say one successful, two successful, three successful, and then multiply those all together.
Well, it's all right.
You wouldn't multiply them.
Yeah.
You would add them. Now, an easier way to do this, because we haven't talked about the addition rule yet, easier way to do this, what did we just find? Probability that all three were unsuccessful was 0.003, right? Well, if all three are unsuccessful, the complement of that, everything else would be that one or more were successful. So what could we do with that 0.03?
Subtract.
Subtract it from
All threes?
1.
just one, the total, right? And you end up with 0.997. So this is probability that all three are unsuccessful. We want the probability that not all three are unsuccessful, that at least one of them are okay. And we just subtract that and we should get it. Now, Cody, you're right. And next time, we're going to get into stuff like that. So if they would have asked us, find the probability that two are successful or one's successful, that group, then we would want to find those separately and add those probabilities together. Here, it's just easier to do it this way. More than 15,000 U.S. medical school seniors applied to residency programs in 2007, of those 93% were matched with a residency position. 74% of the seniors matched to a residency position were matched to one of their top 2 choices. So when you go to medical school, after medical school, you got to do an internship, and that's what this is talking about. And in that internship, you write in there, okay, I'd like to go to this hospital or this doctor, whatever. So 93% of all people were matched somewhere. 74% were matched with one of their choices. The other people just got matched to wherever, and you don't throw a fit because you're lucky to get matched anywhere, because apparently 7% of the people didn't get matched to anybody, and they got to wait another year to do their residency. Medical students electronically rank the residency programs in their order of preference, and program directors across the United States do the same. The term match refers to the process where a student's preference list and a program director's preference list overlap, resulting in the placement of the students of the residency position. Find the probability that a randomly selected senior was matched a residency position, and it was one of the senior's top 2 choices. How are we going to do that? What's the probability that they got matched?
93.
So 0.93. What's the probability that they got matched to one of their choices?
73.
74%. What do you think you're going to do with those 2? Multiply. If we added them, and this is something that'll help. If we add them, what would happen? What would you come up with?
1 point.
You come up with 1 point something. What do we know about probabilities?
Can't go over 100.
Can't be over 100. So we multiply those 2 together and we get about 68, 69% of all the people who applied got matched to somewhere that they wanted to be. Find the probability that a randomly selected senior that was matched to a residency position did not get matched with one of their top 2 choices. So how many of those 94% didn't, or 97, 93%? How many of the 93% didn't get matched to where they wanted to go?
Take whatever that percent was, just subtract.
All right, so it was 74%, right? So what percentage didn't get matched somewhere they wanted to go? 26%. So we did that, 26%. Didn't get matched with one of their choices, sorry. So conditional probabilities, remember independent, dependent. Know if events are independent, dependent. Use the multiplication rule. Multiplication rule just says you find the probability of event 1 times by probability of event 2 times probability of event 3, whatever. As long as they work out that way. That's the assignment. If you guys want, we got about 10 minutes or so.
No, I want to go over.
That's what I'm saying.
Not this, but I want to go over the symbols. As fast as
Can I finish now? If you guys want, we'll go over the symbol stuff. That's what I was going to say, Lily, is what I was trying to get across to you. I wasn't going to jump onto this. Give me some symbols that you should know.
All
All right, once I write this down, now I'm going to sit down.
I just kidding.
Give me a symbol you should know.
Sun.
X bar, What's X bar?
What?
Mean. Now, if you just put mean, I'll mark it wrong. Mean of what? Of a sample. Mean of a sample.
Of a population. Isn't that the O thing?
That?
Yeah.
What is that?
Standard deviation. Population.
Standard deviation of a
Do you
population.
know the names, like of like how you said the menu or whatever?
No, you don't have to. That's not mu. That's sigma.
Okay. 'Cause I was
Mu is the one
I
that
was-
looks like a.
I was listening to somebody else.
And then for standard deviation for a sample, is it just like an S?
What else?
That's squared.
Sum of squares.
And then what's the E thing called?
Best thing to write. Summation. You're just adding all the everything up, whatever comes after. What else? Boy, there's like 20 questions and we got 5. N.
Mean?
Yeah, and
Little n, what's that?
number of
That's,
samples.
Sample
that's
of
the number.
Number.
Of entries.
N.
sample.
Sample. What's big N?
Number of population.
Number in population.
There's something to do with squares, I know.
Mean is the M of population.
And you there, mean of a population.
And then we have already have the sample.
Please, again, make sure that if there's a difference for sample and population, make sure you write out the whole thing when we take this next time. What else?
Wait a minute.
I will tell you this too, some of them on there are like graphs and stuff. You gotta know the name of the graph or the name of the chart or whatever.
So, histogram.
A histogram. Remember, a histogram might look like what? What has to be true?
The bars are touching.
Bars are touching. Now be careful. What if I drew this?
But those have to go
Is that a histogram?
Don't they go from
All
largest to
bars.
smallest?
That's a different one. Are the bars touching?
Yeah, there's just.
Except, what's that tell us about this?
There's no data. There's no-
Alright, there's a gap there, there's no data. So is that still a histogram? Yeah,
Is it cladogram the one where
close. Not Cueto, he was a pitcher for the
Cueto.
Reds.
they go? Cladogram.
Pareto, remember a Pareto graph, what's it do?
Largest to smallest.
And the bars don't actually have to touch. I made them touch there, but they don't have to.
The dot plot.
Dot plot. Dot plot would look something like this. Box and whisker. I'm running out of space. Box and whisker, I'll have to erase this here in a minute. Box and whisker might look something like this.
I think picture so I have this timer for this one, for you to
Got it?
Yeah.
Give me something else.
Variance of the population.
Variance of a population, what's that?
Ohm squared.
What is it?
Ohm squared. Is it ohm squared? Is that how you say it?
Sigma.
Sigma squared. Yeah.
Variance of population, sigma squared.
And then the sample is it S?
The variance of sample S squared
Mean of the sample. Or we already have that.
Is it gonna be like?
Deviation be one? Would that be like a simple or do you?
Yeah, I would put, cause standard deviation is the one that we do with point.
Would like the parameter and like the population be one? Cause like, what they mean each other?
So
So
it's
they
a-
have like the, I guess statistics and then it's like the sample? Or no?
Nah, not for symbols. The symbols are just. Did a whole bunch of stuff there towards the end of chapter 2. You guys haven't got on yet.
CV.
What is it?
Oh, like Z-scores?
Z-score, so if I just put this, what's that?
Z-score.
A Z-score, I would accept that probably. What else went right along with that stuff? You alright, Will?
Chapter 2?
Feel bad? Yeah, it looks so hot. Don't be getting sick in my classroom. Don't be passing out or nothing either. Don't want to have to deal with it. Just kidding with you. Hope you feel better.
Oh, like the sum of squares, like where it's
We did some of the squares, didn't we?
Yeah.
like
Yeah.
this one, I guess. This is just.
Would be okay. Cluster or stratification.
Yeah, that'd be on the definitions. Cluster and stuff like that be on definitions.
Frequency polygon.
Frequency polygon. Frequency polygon would look something like this. Frequency polygon would look, it would have like the dots here. It would connect them all.
Will we have to just like write what this is or like do we have to write a meaning?
Nah, just that, if you can tell me that's a frequency polygon. Sorry, I
What
didn't,
is
I didn't
scatter?
spell out the frequency, but.
And scatter plot
So scatter plot, what would a scatter plot look like?
Just dots.
Scatter plot.
Will the quartiles be on there?
Quartiles. So like what? So Q1, what's that mean? Quartile 1. I'm not gonna write all of them. Then you could have what? Quartile 2. What would a meaning for, if I did put Q2, what else could you write?
Median IQ.
Not the mean.
Median.
Median, or quartile 2, and then quartile 3. More along with that. What else? Say again? Just X? What is just X? X is just a what? It's a variable, that's true, but so if you wrote variable, I probably wouldn't mark it wrong. X is just a term. Something, one, that's like one entry from your sample or your population.
Oh, like, I don't know, I guess frequency would be more, is the F?
Yeah. So what's this symbol? Frequency. don't need to know all the parts. I mean, yeah, you probably do, but know that, let's do this. That says tally, frequency. This whole thing is called a what?
Frequency distribution.
Frequency distribution chart.
Where the PT has a 9 percentile.
So percentile. So how do you write a percentile?
I did it.
P, then what?
P.
Then there's a subscript, right?
Yeah.
So P5, what's that tell you?
That's percentile.
5th percentile. Now don't get that confused with what we've just been covering. Does this mean the same thing?
No.
What's this
What
mean?
is-
Probability.
Probability that you get a 5.
So if it would be P of the subscript like 1, that'd be the same thing as the first percentile?
Yeah, so that'd be the first percentile.